Good morning, everyone. I'm Diana, and I'm the Marketing Communications Manager here at Norsat. On behalf of the company, I would like to thank you for joining us today. Our presentation today is on 5G LNB, which will round out this year's monthly webinar series. I'm very delighted today to introduce our presenter, Dr. Jaber Moghaddasi. Dr. Moghaddasi received his PhD in electrical engineering from the Polytechnique Montreal School of Engineering at the University of Montreal in 2017. He has authored several peer-reviewed papers and holds 3 patents and is a recipient of several international awards, including the 2019 IEEE Microwave Theory and Technique Society Microwave Prize. His previous stints include working at BlackBerry and serving as a co-op research engineer with Huawei. He's currently working with the R&D team here at Norsat as an RF design engineer. So we'll begin the presentation, after which I'll open the floor out for questions. Please use the question box in your control panel to submit your questions throughout the webinar, and we'll address them towards the end. And just a few housekeeping items. If you're not currently subscribed to a newsletter, please do so you can stay updated with all of our latest events, webinars, new product launch announcements, and company news. Now, without further ado, I'm going to pass things off to Dr. Moghaddasi.
Thank you, Diana. Hello, everyone. Welcome to today's webinar. I hope you enjoy today's discussion. Before going through the slides, let me quickly introduce to you what we're going to discuss about. First, we're going to talk about this new technology and new era of wireless communication. We will talk about the impact of this exciting technology on SATCOM terminals. Following that one, we will talk about the problem of interferers, blockers, and the common techniques in designing blocker tolerant receivers. The impact of 5G interference with satellite terminals will be studied more in detail. I will demonstrate some impact of this through some measurements on a normal satellite terminal. The possible solutions specifically for this LNB, for these satellite terminals, will be reviewed. And also the performance evaluation or figure of merit actually will be discussed. We will tell you from different angles, we actually measure the performance of this kind of LNB. There will be, as promised, there will be a live demonstration of the performance of this switchable LNB, named as 3200 SBPF-5. And at the end, I will compare a couple of solutions that I have actually put forward via system level test or loop test by measuring bit error rate, EB over N0. Finally, I will just introduce you the references, and I'll be happy to answer your questions. Well, we are all entering new era of wireless communication. 5G or even beyond 5G has been much publicized, and this technology is really huge and massive. It is covering from automotive and autonomous driving systems with communication rate in the range of a couple of kilobit per second between vehicle to vehicle, up to millimeter wave up to 52.5 gigahertz for now discussed. Where they have gigahertz in bandwidth in the range of gigahertz for very high data throughput. In its initial phase, it has been discussed to start from lower frequencies right now below 7 gigahertz, and it is going to be designed for now to be operating alongside the 4G LTE with common carriers. Of course, some whole capacity on this frequency range is going to be used. Wi-Fi and its license bands is going to be used for this technology. In addition to the available bandwidths of around 3.5 gigahertz. This frequency is very familiar for, very well known for people working in satellite industry. This is called a C-band. This is a typical frequency band which was discussed for an auction for selling this C-band communication frequency range. So we can see that up to 3.98 in some areas can be sold out. I know that this is going to be worldwide and different zones and different places. This frequency available for 5G may differ, but depending on your and the scenario of application and where we use our satellite communication terminals, 5G can impact our SATCOM application. Like I said, even though this 5G is very interesting and everybody is excited to see very soon, but this has some negative impact on satellite terminals. Easily, as I said, frequency channels have been sold out for this frequency, so narrower bandwidths are available for C-band communication. These strong 5G signals from 5G towers may have some impact on our satellite terminals, specifically LNBs. How strong this, how they may block our LNBs, it really matters and actually depends on the distance between our satellite terminal to the tower, 5G towers, the azimuth and the elevation angle between the antenna bore side, the dish bore side to the satellite, and also the angle between the dish to the 5G tower as well. So a case study, just a rough calculation. If the 5G tower has the power of around, EIRP of around 34 dB watt, if it is in the range of 150 meter, the available signal power from this 5G can be around -25 dBm. This is far above the normal satellite signals, which is normally around -80 to even -110. So, like I said, this problem of blocking receivers is not really new, even though it has been much discussed for satellite communication. Coexistence, it was well known about coexistence, multimode radios, or about very wideband receivers for software-defined radios. Always a solution for designing such a receiver was of a point of interest. They're very important. The two principal mechanisms of this blocking the receivers, I can name it as gain compression or reciprocal mixing. Gain compression actually happens in the early stages amplification, where strong signal is present at the input of the receiver. This basically clips your amplifiers and saturate them and makes a problem. On top of that, there's a mixing between your blocker signal with your LO, which is called reciprocal mixing. In next slides, I will show you how they may impact your receiver. There are some techniques, to be honest, has been discussed, much discussed. Numerous patents have been filed on this. I'm not going to talk about them here, but most common ones are filtering, which is not always the best one. Some more innovative techniques called as passive mixer first receivers or empath filtering is really hot topic of research and is becoming a reality. On top of that, or in addition to that, there's also some technique called noise canceling. In the second one, as named as passive mixer first receivers, actually, instead of having amplifiers after the antenna, we have right way mixers. We down convert them, and because these structures are called impedance transparent, all filtering happens in the baseband. Well, it's being transferred to the LO, around LO, becoming a bandpass characteristics. Having a bandpass characteristics. Noise canceling is nothing more just having a feedback and canceling the voltage gain of your amplifiers around the frequency of your blocker. For these second and third structure, we don't need filters. However, for these structures, as far as I know, I couldn't see anything better than 2 or 3 dB of noise figure. This is actually, I mean, hilarious for satellite communication. In C-band, we are really interested in noise figure of around 0.4 dB or even less if we can. So let's focus on the impact of blockers on this C-band satellite terminal. This architecture is actually a typical LNB architecture for C-band satellites, covering from 3.4 up to 4.2. When it is down converted, it goes down to 0.95 up to 1.75 if the whole bandwidth is being used. If this standard satellite is being used for this new scenario where 5G signals are present, you will see that a very strong signal in the range of -20, -30 dBm at a frequency not very far away, only 100 megahertz, namely 3.6 gigahertz, is present at the input. When it is amplified and down converted, it goes to the output and appears next to the final frequency at the L band. Look at the terminologies. I will keep repeating these terminologies. When we say interference leakage, and we talk about this at the IF, that we have to keep an eye on it. If we use this receiver or this LNB for this new scenario where such a blocker is present, instead of having a clean signal right in the middle of frequency, or only in this range, we will see multiple tones and spurs, which is the result of presence of such a blocker at the input of your LNB. So I talked about the mechanisms, and let's talk more specifically about what happens in the LNBs. When such a strong signal is present,
just sorry, interjecting. I think your webcam it froze, so if you don't mind just restarting that.
Okay, so thank you for saying that. Let me stop it. Is this good now?
Yep, you're good. Thanks.
Okay. Yeah, so performance degradation actually happens mainly because of a couple of things, actually. The first thing is that these amplifiers, they have voltage gain and these strong signals. What happens is that this strong signal will clip this amplifier, so they will saturate it, and saturated amplifiers can cause many problems, including no more gain or introducing to more products. As I said, another problem very important here is the reciprocal mixing, which is a result of mixing of this blocker signal with this LO. It is not specifically a straight LO minus RF. I will show you what other higher order mixes can also be present. Obviously, if your LO has a phase noise, well, maybe it's not the case for a satellite, which is very far away from this case. But in general, in blockers, in blocker tolerant receivers, if the LO is very close to this, the phase noise of the LO will really matter, because this will shadow, it will be down converted next to it, and it will shadow your desired band, right? So this can increase your noise figure. Another thing which is important is the leakage. Like I said, this is strong leakage. It can be present, and if it is not controlled properly, it can saturate your modem or your ADC of your receiver at the end. Let's see the problem first before offering the solutions. This is, like I said, is a standard LNB, or maybe an LNB that does not have a proper tolerance against blockers. Around the C-band satellites, normally a couple of frequency bands are being discussed about possible interference signals or 5G signals. One of them is, like as I showed you, is below the operational band, It can go down to 100 meg or even 20 meg in some scenarios. In this case, if it is a 3.6 gigahertz here, very weak, not minus 25, it may show up as I said. So this is what I showed you as interference leakage. And this is what pops up in your when you monitor the spectrum. Also on the other side of the band at 4.8 gigahertz, there can be some spurs, some undesired tones that can show up in the middle of your frequency band. Let's see, it actually makes sense. It's just a very simple calculation. It's from a spreadsheet. You will see that this really agrees with this higher order mixing, 4 times RF minus 3 times LO for the 3.6 gigahertz. Well, quite by accident, at 4.8 also this is happening. And the same frequency. Obviously, two things. If it is wideband, this will spread out. If it is at different frequencies, actually this will come up with different frequencies. It is predictable by this simple calculation. Another conclusion that we can get, don't forget, we don't have any in-band signal. This is just a noise level, actually noise floor that comes up at the output of your LNB. This is not a result of mixing between your log curve and your desired signal. You don't have any in-band signal. This is only a result of mixing between your LO at 5.15 gigahertz and your frequency. Well, I put this one as a desired signal to have this calculation. So what is really the optimum solution for satellite receivers? Again, I'll brought the receiver block diagram. When coming up with a solution, we actually keep an eye on a couple of things. First of all, we claim that we want to have a blocker tolerant LNB with no degradation. What does that mean is that looking at our technical spec, noise figure of 30K, gain of that, P1 dB of this, Spurious level of that one, all of them should be preserved in the same if we can, or at least minimize the impact of it. So we keep an eye on a few things. We will see how much noise figure is actually degraded. We are actually, if you're using filtering technique, as we said, we just agreed that this could be really the best solution for this kind of receiver. We should have an eye on the gate flatness. We don't want to miss 1 dB per 36 megahertz. Input VSWR will have an impact on it if you want to decide where to put the filter. Interference leakage at the output, as I said, it should be below some level that does not saturate our modem, namely this minus 10 dBm or so. What is really the maximum input interference power level? Is this going to be limitless or there's a limit? We should keep an eye on our spurious level. We don't want to limit our SFDR. Another interesting parameter which is really defined in designing this kind of receiver is called blocker 1 dB. We normally have P1 dB, which is really the power level at which your gain actually drops by 1 dB. But we also have a B1 dB, which is called blocker 1 dB. What does that mean? It means that you have your in-band signal, but you also have a blocker. If you're designing a receiver which is named to be blocker tolerant, you should find out what is really the maximum blocker power level that degrades your gain by 1 dB. So there's always a limit for that one. Our conclusion is that they could, for this objective, keeping all of them in an acceptable level, filtering is one of the things that can be applied, and also improving the linearity of our receiver. For filtering, optimum place should be find out. We'll discuss about it. Where really to put the filters. Is this either here, here, or here? This really matters. I will show you in the next slides.
Sorry, Jabber, your camera is also frozen again. Maybe it's just, yeah.
I apologize for that. I don't know what is there. Is this good now?
Yep, you're good.
Yeah. So there are four available solutions that Norsat has put forward. External waveguide filters. We have some LNBs actually, which has integrated filters somewhere in between these chains and mixers. We also have a LNB with switchable filters that we can have two LNBs in one actually LNB basically. In some scenarios that this LNB with integrated filter is not good, maybe a hybrid solution should be used. So there are actually two types of filters. You can find it in our website. They're called BPF-C and EBPF-C. This is for the case that is covering the narrower guard band, either below or above the desired frequency range. We have multiple versions of that, from -1 up to -6. Each of them are covering a specific frequency band. Obviously, this one has more rejection, but it comes with the expense of more weight and also larger size, and also the worse group delay. Speaking of guard band and rejection, let me show you the spectrum and compare, the frequency response and compare the performance. This is what we call the guard band. You see, this is EBPF. Obviously, it has more rejection, very close to the operational band, whereas the other one is providing actually the same rejection in a further distance from the operational band. So looking at some numbers, we will see that this comes with the expense of having more insertion loss. If you use EBPF, it can go down to 1.4 or 1.5, worst case, when it is only 150 megahertz away from the center frequency. By the way, this is the reference. But at only 18 megahertz or 15 megahertz away, we have 15 dB rejection, right? Whereas this one does not give you the same rejection. It's only happening, same rejection happening at 100 megahertz. So the optimal filter can be selected based on the application. So now let's look at the solution number 2, LNB with integrated bandpass filters. So our studies and investigations confirmed that the best and optimum solution to maintain all other parameters, including noise figure, input VSWR, and Spurious level, and so on and so forth, and acceptable is to place a filter right after the second stadium and third stadium. This helps us to prevent saturation of these LNAs and also this mixer, control the signal level that comes up with the mixer input, also improve the linearity of this one so that we can have we can gain something from this one because it's more linear, so no reciprocal mixing. Also to control the output leakage level, we gotta control this with more filtering. We can do that with some low pass filters. This is how it looks like a typical 5G LNB. This is a frequency response or gain of an LNB. Because I normally receive some questions what this really means. For some audience that are not familiar with it, let me just quickly go through it. This is inverted, first of all. If I talk to about 3.6 gigahertz, 3.6 gigahertz is inverted comes to 1.55, right? This is a rejection level that I showed you about the filters. So this LNB has some rejection. It's around 50 dB rejection at 3.6 gigahertz, which is now at IF frequency. L band is around 1.5. So this is with reference to the edge of the band. We also monitor the gain flatness here. This is the beginning of the band. This is the end of the band, 3.7 up to 4.2. We will see that all the way up to 4.8, we preserve this rejection. Also below 3.6 gigahertz, we maintain this desired rejection. So this is the measured gain. We will see this many times in this coming slides. Another parameter, like I said, for evaluating our LNBs, we actually examine them through different angles. One of them, as you just saw, is the frequency response we gain. Another one is the spurious level test, which is very important. Maybe some of you have seen already test with CW signal. This time I measured them with modulated data. So this is a typical blocker, which is modulated by QPSK 10 megasymbol per second. We pushed it hard to 3.79. So this means that the closest frequency would be right at the edge for the case that we are actually planning to protect 100 megahertz away as the guard band. This is for 3200 dpf-5. Obviously, it has narrower bands. And if we move forward in the higher frequencies, as for this blocker, even with 20 megasymbol per second, we can see that we do not lose our 50 or 55 dBc interference level. I will show you in some the next slides how I'm testing these things. Let's just imagine that this is for the case that we have both the desired signal, we're pushing it hard, that somehow that we have minus 10 dBm at the output, and also we have the blocker at this power level that we can control it at the input of the LNB. But the conclusion of this one is that either CW or modulated signal, still this solution, this integrated 5G LNB, is immune against. Like I said, there are a couple of figure of merits, but we should be mindful about it. I received many questions about this frequency response of the LNBs. I can tell you that this is not the best and the only figure of merit to examine which solution is really a good solution. This is comparison between an LNB which has integrated filters, and also another LNB has also some integrated filters. But it really matters how this has been designed. So I'm comparing this. You can see that at 3.6 gigahertz, both LNBs have the same rejection, minus 50 dB, which is awesome. I named it as LNB1 and LNB2. If we compare the spurious level, we can see that LNB1 is very immune, and, even though we have this leakage, so we are still preserving this 55 dB rejection. Whereas the other one, which had the same rejection level, is completely cropped by this interference signal. We have 30 dB gain reduction. This is the main band signal. You see this one. Many other tones, which we named it as spurious, are present. This LNB is not usable. Yeah. So another solution, as the third solution, was the LNB with switchable filters. The typical application of this switchable LNB that we will see a lot about it in the next slides is a maritime application. Imagine a scenario for maritime or anything else that you want to switch between two bands. If you're far away from the seashore, there's no 5G signal, you want to use and enjoy the wide available bandwidth of satellites, so you can just switch to the standard mode. Your 800 megahertz of C-band satellite communication is available for you. But if you come to the seashore, of any condition that blockers are actually blocking our LNB, we can switch to the mode which is immune against it. So this is a typical architecture or PCB of this LNB. As promised, we were supposed to demonstrate their test bed and also see that how we really examine them. So let me run this. This is a recorded video. Well, it's not live, but it's a recorded video. I will talk over them. Yeah, I'm just showing that this is the DUT. This is the LNB, and this is fresh out of the box, switchable LNB, which looks exactly the same of standard C-band LNB, and also the LNB with 5G integrated filters. Sorry, the integrated bandpass filter. It's biased from the power supply, and there's a PNAX. For the output, I'm going to measure the gain. When it is in band 1, we can see that it's very wide, marker 1, 950 megahertz. This is the beginning of the band, but we see that we have 800 megahertz here in band 1, or mode 1. that we don't need any rejection or any immunity. So I will be waiting to see that when we're going to switch to band 2. Yeah, so as you can see, when I go up to 18 volts, we can see that we have switched to band 2. We have the desired rejection. Marker 2, look at the marker 2. This is with reference to marker R here, which has 50 dB, showing 50 dB rejection, and it actually is preserved across the whole possible 5G band. Another thing that we keep an eye on it, we don't want to see lots of changes and gain in the common portion of the band. So this is going to be preserved around 2 dB or 2.5 dB. Also, the gain flatness will be started just focusing on this narrow bands, making sure that this 1 dB per 36 megahertz is preserved. So this is one test that shows how this switching is actually functioning. By the way, we kept that one in memory to just compare. This is just a memory. So this is another test. I showed you many slides demonstrating that we have a blocker, we have an advanced signal. And you're on this video. Yeah. So this is basically how we test this. This is the DUT again. 2 signal generators. One of them is the source of main signal, resembling the in-band satellite signal. Another one is the source of interference on the right side. We monitor the spectrum. It goes to the spectrum analyzer connected to a screen, larger screen to show that. So the power combiner at the input of the LNB actually tells us that this combines these two signals. We make sure that the loss of the cable and also the loss of this power combiner is actually included when we measure our input power level. What really matters is just to see that the input power level to this LNB is, how much it is. So right now we are in band 1, 13 volts, and there's no interference, everything is off, there's only main band signal. So now I plan to turn it on. I turn it on, well obviously this noise floor is increased to make it fast sweep. So at even minus 50, minus 55 dB, we see that this blocker has just popped up. And the main, we named it as leakage, right? So right now it sounds like there's no problem, even if you believe that leakage level is good. But when we increase it, you see the gain drops and other spares are popping up. When we increase it even more, probably it's around minus 40 or something. LNB is not usable. So this, we lost our main signals. Other tones are present. We probably have already saturated our ADCs, and we have to switch to band 2. This is how we switch it. Actually, we don't need to tune it gradually. We just need 2 voltages. We have moved to band 2. Everything is corrected. Our main signal is come up to the desired power level. This is again our interference leakage, right? So we have controlled the power level of this below minus 10, minus 20 or something. And now we are allowed to even increase this power level, probably minus 20, minus 35. We turn it off, turn it on, nothing happens. I feel like our LNB is functioning as there's no blocker signal. This is what we call it the spurious level test. And also we keep monitoring the output power level to be below the acceptable power level based on the modem specification. Yeah, so another test is that this is a short video, Spurious level, how we test this 55 dBc. We are in band 2, and we see, let me run it. Yeah. We've just brought down this noise level, controlling this power level of this one. Again, we have this leakage, and we will see that we have this 55 dBc rejection just to make sure that our SFTR is not gone. So we just pushed it hard to higher levels. You see that this spur has moved. This tone it is stronger now. Well, this is probably beyond the limit, and which is not acceptable. So this we lost our 55 dBc rejection. Every solution can have limits, right? So there are actually two limits we always talk about it in our data sheet. One of them is that what is the maximum interference signal level? The other one is the maximum interference or blocker power level. Some numbers like 100 megahertz away, or also this minus 25 dB, maybe some of you have seen in our data sheet. So we are in band 2. We turn on this spur, as we said, minus 25 dBm, again at the input of this LNB. Right now it's functioning properly, but is it going to function for all power levels and also all frequency crossing? No. We keep increasing the power level of our blocker signal. You see the degradation of gain, frequency response, and at this point, your LNB is not going to function. So this means that minus 25 or minus 20, which is promised, should be maintained. Another parameter is that it really matters how close you get to your operational band. That's what I call 100 megahertz guard band. So when we see that I'm just changing the frequency of our blocker signal, I'm getting basically closer to the operational band. And instead of 3.8 gigahertz, I'm going to have a 3.85, for example. And getting it closer and closer, we see that this LNB with integrated filters is not immune against it anymore. So this limit should be preserved. One of them is maximum power level. The other one is that any solution that you select is either it's an external filter, or it's an integrated filter, or it's a hybrid one. You should keep an eye on the limits, how close we are, or what is our guard band. This basically defines the challenge in designing such a receiver, and this will give us a limit. So of course, so we're done with those videos. Of course, if we test this Spurious level with the modulated signal, it really doesn't matter. It doesn't have an impact. This LNB band 2 is still immune, even with this modulated data. At last, I want to talk about. Now we have demonstrated multiple solutions: external filters, integrated filter, LNBs with integrated filters. The switchable one, and also the hybrid. Well, I've not demonstrated the hybrid one, but obviously you could combine them in some extreme scenarios that we have very strong 5G signals. We can use both of them. For this comparison purposes, I am actually comparing multiple solutions. One of them is BPF plus BPF filter, external filter, one, plus a standard C-band. This one is BPF band 2, so now we have like a 5G LNB. This is 3200 BPF-5. Like I said, it doesn't matter. It can go from different frequencies, but now I'm focused on this option. Interesting. This is another 5G LNB, which has really extraordinary frequency response, way more rejection, even more than the combination of the external filter with the standard C-band LNB. So in the following slides, I'm going to compare these ones, and also in a system level test or loop test, I will see the way that we were measuring it, how it agrees with with the real scenario performance. So before going through the measurement results, let me just quickly show you how I was testing it. This is a loop test. I know that in a loop test, in this particular rate test, it can go easily very wrong. So the condition, because I wanted to test all of them in 15 in one day, so I kept an eye on it, absolutely 15 minutes for testing it. And we are reading the EV over N0 at the modem. We're measuring the bit error rate, which is connected to this modem with this bit error rate tester. Modulation of our main band signal, I put it right in the center frequency. So it's at 1.1 gigahertz at the L band. I modulated this QPSK is common at 2 mega symbol per second. And I'm pushing these LNBs very hard at 3.8 gigahertz. Like I said, we just saw that it really doesn't matter either it is a CW signal or it is a modulated signal. This is the measurement result. We can see that this switchable LNB in band 1, which is basically an LNB without any protection, it fails. The bit rate actually degrades significantly in power of -50 or -55 dBm. And way above that, your LNB loses the sync, as not function. So other solutions, including the 3000 LNB standard plus the external filter, and also our 5G LNB, and also our switchable LNB in band 2, we see that after up to -25 dBm degradation is actually acceptable, it's really minimized, while up to -20, this really degrades significantly, and after that it loses lock. One thing that I forgot is that in our to tell you, our LNBs, B1 dB, or the signal power at which our LNB will lose the gain by 1 dB is around -18 dBm. Again, it's different from P1 dB. Interestingly, you can see that you remember the frequency response of the LNB with extraordinary frequency response and extreme rejection, even more than this one. And I told you that it really matters where you're actually placing your filters in your LNB, and we should not be distracted by only taking into account frequency response as a figure of merit. We can see that that LNB integrated with integrated filters is obviously failing at even -30 dBm, so it can be functional only at -35 dBm. And right above this ones, this is not usable at all. So this was measured with the bit error rate. At the same time, we were actually keeping an eye on the EV over N0. We never measured the noise figure after that for some reasons, because our noise figure meter will actually get saturated. So we don't really trust when we combine them to measure the noise figure. But this gives us a good insight. All measurement solutions that I discussed, and said that we measured them from different angles, spurious level frequency response. This actually confirms that. Through other tests, we concluded that our LNB is immune up to -25 dBm. Amazingly, this is actually confirming it. Up to -25 dBm, they're actually this is functioning with minimum degradation, and up to -20, well, it cannot be acceptable by this much degradation. Again, I took one as a reference, and this is degradation. This is not EV over N0. So we just see that how much we're failing when we go up into when we increase the interference power level. So this confirms that our conclusion about -25 dBm maximum coming up from the Spurious test or other ones is acceptable. Loop test has confirmed that, and standard LNB with no protection absolutely fails far away at -60 or -50. The LNB, amazingly, the LNB would have a better rejection performance. Again, it failed below -35 dBm. So with that being said, there are multiple references. I decided not to have very technical discussion today. I mean, because I was not sure about the background of the audience. If you're interested, 5G and health, you can go through this this interesting reference. Studying about other techniques, these references are found very interesting. There are many other ones. If you want to taste a glimpse of new wireless, modern wireless receivers, this is a paper of mine just published recently a couple of weeks ago. I'm reviewing all existing techniques and all these discussions in a review paper. For about satellite and 5G LNBs, just do check our website. There are numerous application notes, white papers. And there's also another webinar presented by our chief scientist, Mr. Jeffter. Please check that one. So with that, I will conclude my presentation, and I will be happy to answer your question. Thank you for your attention.
Thank you, Jabber, for that presentation. And now we would like to open the floor up for questions. If anyone have questions, please submit them in the control panel, in the question box in your control panel, and we'll address them.
So can I see the question, or?
Yeah, just they'll pop up on the control panel. So we don't have any questions as of now. Okay, it doesn't have to be questions related specifically to this presentation too. If you guys have any questions for Jabber too, feel free to submit them in the in your question box.
Yeah, as promised, I decided to finish my presentation quickly before 45 minutes.
Yeah, you're right on time. So good timing on that. Okay, well, yeah. If there are no further questions, I will conclude the webinar. But before I do so, just kind of want to just a few more housekeeping items. Please fill out a brief survey that we'll send out to you after the webinar and let us know how we did. If there are specific topics that you would like us to cover in the future, please let us know. And the next webinar, so this is the last webinar that we're doing for the rest of this year. And then the next webinar will begin again in January. So yeah, thank you all for joining us today, and I wish all of you a wonderful holiday. Hope all of you keep safe wherever you are, and thank you, Jabber.
Thank you. Thank you all for joining this webinar.
Okay, bye everyone.